Here's an introduction to the idea of improper integrals. First, we'll start by looking at type 1 of the two types of improper integrals. As an example, let's find the area under the curve of the function f of x equals 1 over x and the function g of x equals 1 over x squared, both on the infinite interval from 1 to infinity. So before we can actually find this area, let's start by looking at a graph of these two functions. Let's start by graphing the function f of x equals 1 over x. This is pretty straightforward. We know that when x is 1, our f of x is also 1. And as x gets smaller and smaller, closer and closer to 0, this function is going to go off to infinity. 1 over 1/2 is 2, 1 over 1/3 is 3, 1 over a very, very tiny number is very, very large, and so on. And as x gets bigger and bigger, 1 over x is going to get smaller and smaller. We're going to get closer and closer to 0. So we're going to have a curve that very smoothly and nicely approaches the x-axis like this. And we're interested in the area under this curve on the interval from 1 to infinity. So let's cut this off right here. And let's shade in the area that we want. That will be the area right in here, going all the way as far to the right as we can. We'll never ever stop going to the right. We have an infinite, unbounded region here whose area we want to find. Now this is a little odd because it might be that our area turns out to be infinite. After all, the area above that curve is certainly infinite. It goes off infinitely far up and to the right. The area under this curve is finite in height, but the region goes infinitely far to the right. But it gets smaller and smaller and smaller as we keep going to the right. So it's possible we may have a finite area in here, but it might be that we have an infinite area. We're not really sure. We'll have to do a bit of work to figure that out. Before we do that, though, let's look at our other function for comparison. We also want to find the area under the curve of 1 over x squared. So let's graph that as well. That is also going to go through the point 1, 1, because when x is 1, 1 over 1 squared is still 1. But what about x values that are larger than 1? If I were to look at the example 2, for instance, the height of the red curve when x is 2 is 1/2. But the height of my new green curve that I'm drawing is going to be only 1/4 because 1/2 squared is 1/4, or rather 1 over 2 squared is 1/4. So this green curve in general is going to be smaller than, lower than the red curve everywhere to the right. So it's going to approach the x-axis, but it's going to do so more quickly than the red curve does. But it will still never quite reach the x-axis. It'll just get closer and closer. Going to the left of the 1, well, smaller numbers between 0 and 1, when you square them, get smaller, which means 1 over those numbers is bigger. So this curve is also going to go off to infinity as x approaches 0, but it's going to be higher than the red curve. Looks like that. So they are similar kinds of curves, but they are not quite the same. The red curve is actually symmetrical, diagonally speaking. You can swap the x and y axes, and the red curve will be the same. But the green curve gets close to the x-axis very quickly and takes longer to approach the y-axis. Here is our g of x equals 1 over x squared. So the area under this green curve is the area of this region in here, which is again an unbounded region that goes infinitely far to the right, because we are not, even though my picture cuts off at a certain x value, my actual graph goes off infinitely far to the right. I'm looking for the area under the curve when x goes from 0, or when x goes from 1 to infinity. So there's no upper bound to the x value here. But it might be that our area might still be finite. We don't know, because that little tiny sliver of area that gets smaller and smaller as you go to the right may actually have a finite area in total. We're not sure. How do we figure this out? The problem is that we know how to define the area under a curve as a definite integral, but a definite integral by definition requires that it be defined over a closed interval on the x-axis. You could do an integral from 2 to 5, you could do an integral from 1 to 20, you could do an integral from 1 to 5 million if you wanted to, but an integral from 1 to infinity doesn't really make sense. So the way that we'll solve this problem is as follows. Let's pick some arbitrary upper bound here. Let's call it t. Now I can find the area from 1 to t by taking the integral from 1 to t of my function, which is 1 over x dx. That's going to give me an area that is not the total area I want. It's clearly not because there is some part missing. The part to the right is missing. But what I can do is I can then shift that t over, move that t further along out to here, and fill in more area. And I can keep doing that forever. I can keep pushing my t farther and farther and farther to the right and add in more of that missing area. And I will never end up with an infinite area, but I can look at the limit as t goes to infinity. So this is what we'll do. We'll take the limit as t goes to infinity of this area. And this is going to give us our total area. And the notation for this, we'll just call this the integral from 1 to infinity of our function. So let's just look at this definition written down more explicitly, and then we'll talk about actually solving the problem. So by definition, if we want to find the integral, a definite integral over an infinite interval, the integral from some finite number to infinity of a function is defined as, well, we'll just take that upper bound, change it to a variable, call it t, the integral from a to t of our function, which is defined, and then take the limit as that upper bound goes to infinity. And that will give us the area under the curve from some finite starting point all the way out to positive infinity. Alternatively, if we want to find the area from minus infinity to some finite upper bound of our function, we'll let that lower bound be a variable, call it t, and find the integral from that t up to our upper bound of b of our function, and take the limit as t goes to minus infinity. So we'll just keep pushing that lower bound farther and farther and farther to the left and see what we end up with for our integral. In either case, these limits might be finite, in which case the integral is equal to the value of that limit, or these limits might not exist, or they might be infinite. And if either of those things is the case, if these limits come out to be infinity or minus infinity, or if they are just nonsense and don't exist at all, then we'll say that the integral diverges and therefore does not have an answer. So let's actually do this for our problems. So we're looking for the integral from 1 to infinity of 1 over x dx. Now, this is a pretty easy integral to do, except don't forget that upper bound is infinity, and that's not really acceptable in an integral. So the first thing we should do is we should change that upper bound to a variable. Let's call it t, the integral from 1 to t of 1 over x dx. And we'll want to take the limit as t goes to infinity. So now let's actually work this out. We'll leave the limit till last, limit as t goes to infinity, of the integral from 1 to t of 1 over x dx. This is an easy integral. We're going to end up the natural log of the absolute value of x, evaluated at 1 and t. Let's fill that in. Again, we have not yet computed this limit, so I need to keep writing the limit expression here. Limit as t goes to infinity of the natural log of the absolute value of t minus the natural log of the absolute value of 1. Now, this last part here is very easy. The natural log of 1, the absolute value of 1 is 1. The natural log of 1, what power can I put on e to get 1? The answer is 0. So that whole part goes to 0. And furthermore, if t is going to infinity, then we certainly know that t is positive, so the absolute value signs are not doing anything. So we have really the limit as t goes to infinity of the natural log of t. And that's very easy. We know what the behavior of the natural log function is. As the variable goes to infinity, the natural log also goes to infinity. What power can I put on e to get something close to infinity? I have to put power close to infinity. So the answer to this is infinity, which means our integral does not equal infinity, because an integral cannot equal infinity. It has to equal a number if it is anything. So what this tells us is that our integral diverges. And it does tell us that the area under that curve is infinite. Let's go back and look at our curve and see. So what this tells us is, if we look at our curve, this area here is infinite, which means that even though that y-coordinate, the height of the curve, is shrinking, shrinking, shrinking as you move to the right, the amount of area that you keep tacking on as you keep pushing your upper bound to the right is enough to keep causing the area to get bigger and bigger and bigger the wider your interval goes. As we go out to infinity, the amount of area under that curve is actually infinite. Let's look at our other function now. So g of x equals 1 over x squared. This function looks very, very similar. It's still an unbounded region, and the y-coordinate is going to get closer and closer and closer to the x-axis as we move out further and further to the right. This region is still unbounded, but that excess area that you'll keep adding on as you move your upper bound further to the right, is that one going to give us an infinite area, or might it actually be finite? Let's check. We can compute the integral and find out. This time, let's find the integral from 1 to infinity of 1 over x squared dx. So as before, the first thing we should do is we should convert this improper integral into a limit of a proper integral in which the upper bound is a variable. So we're going to change that upper bound to a variable. You can call it t or anything else you like. It's traditional to call it t. So we'll go from 1 to t of 1 over x squared dx. And we'll take the limit as t goes to infinity. Let's work this out. First of all, 1 over x squared is actually x to the negative 2. So if we want to find the integral of that, the antiderivative is going to be negative x to the negative 1. That's going from 1 to t. But we're finding the limit as t goes to infinity. So we'll fill in our bounds. This is the limit as t goes to infinity of, let's see, negative x to the negative 1. That means we actually have negative 1 over x, but our upper bound is t, so I'll fill in t here. Now, minus a negative, that means plus 1 over our lower bound, which is 1. So what we actually have here is the limit as t goes to infinity of 1 minus 1 over t. Well, as t goes to infinity, 1 over t is going to go to 0. So this part here is going to go to 0. We'll have 1 minus 0. Our answer is actually 1. So this integral actually converges. And the area is actually 1. So for this region, this area here is exactly 1. Notice, of course, if we'd changed our lower bound, the area would be different. If we changed our lower bound to 2, we would chop off a part of this region and have a smaller area. If our lower bound were lower, say 1/2, we'd end up with a little more area to add in here. So our area would actually end up being bigger. Right? So the area depends on both the lower bound and the upper bound. In this case, if the upper bound is infinity, which isn't really a bound, then our area still depends on what the lower bound is. But in this case, we can have some unbounded regions, like this one, that go infinitely far to the right, but because they are so thin and tiny as you go to the right, they're thin enough and they shrink fast enough that the total area ends up being finite. In this case, the area ends up being 1. So one more time to review what we did. We were trying to find an integral from some number 1 to infinity of a function. And what we did was we converted that integral into an integral where we replaced the infinity, the upper bound there, with a variable t. That now is a definite integral we can solve. And at the last step, we took the limit as that t went to infinity after we had computed the integral. We either got a number, in which case the answer was a number, or we got something infinite, either minus infinity or positive infinity. Sometimes you'll do one of these integrals and you'll get an answer that is neither infinity nor negative infinity, but still does not exist. In either of those cases, we'd say the integral diverges. And that's how we solve these kinds of problems.